the real world times we study it are ridiculous when we actually have a current. But between the parallel plates of capacitor, we don't actually have a current. So that's the situation where it becomes important that we understand this thing called the displacement current, the magnetic field from the displacement current. Any other time, I'm not going to have you calculate because it's silly to calculate something that is 12 orders of magnitude smaller and add it in. Okay, I got a value of the magnetic field of 5 Tesla due to the actual current. And now I'm going to figure out the current due to the displacement current. 5 times 10 to the minus 12. Okay, so add 5 to 5 times 10 to the minus 12. What do you get? 5, right? 0.0000011 digits later, you finally see another 5. So it's ridiculous. If it's the only thing there, that's different. So that's why we're in situations where we study it, we separate that part. Even though the book will have you calculate both on occasion. So then the book goes on, at this point, the Achieved book is categorized differently than our textbook. Our textbook starts chapter 33 with electromagnetism as a wave. And that's the part, but I knew they were combined here, that's the part last time where I showed you the partial differential stuff because I knew it was encased in this one, right? We don't do a lot with it, but it's nice to be able to do the math and see where it comes from. Because if you are an electrical engineer or some type of other glutton for punishment like a physicist, you have to be able to do those things, right? So they basically said, hey, electric fields generated by electromagnetic radiation are sinusoidal in magnitude. They're sinusoidal in magnitude. So the visible light coming out of that thing has an electric component which is sinusoidal in nature. Whether we generate it with a DC current or an AC current does not matter. Its electric field will go up and down in a sinusoidal manner. So again, it's unpolarized initially, we talk about polarizing. So it has an X component, a Y component, and a Z component. But generally the Z component is the direction of travel. So generally we call this one we don't generally call this the Z direction, we call this the X direction, this the Y direction, and then the Z direction would be out of board. So if we study an individual wave, we're only studying E as a function of X and Y, a plane wave that happens within this wave. And then of course there's a time dependence to it. So as we studied in Physics 1, this used to be Y as a function of X and T. So this X, E value, will actually be the Y component. How much of it you have in the Y is your E. Then depending on which part of the wave you're looking at, you will have a Y2 corresponding, or a Y1 corresponding to that X position of the wave at a time. This wave will travel so that a time later, T plus delta T, T plus dt, the wave will look like this. So this X2 position will have a new value for Y2 at this point. So it's very hard to put both of these waves on the same axis. One is E as a function of, E as a function of X, the other is E as a function of T at a different time. So that's why we saw in Physics 1 to study a traveling plane wave, Y was a function of X and T, and it was sinusoidal. We used Ym sine Kx minus omega t plus a phase angle, so it could start anywhere. It didn't have to always start at a maximum at 0. It could start anywhere we wanted to, right? So that Y was then a function of both X, and then for any individual X1, we would have to grade its y as a function of t graph. And this guy would vary sinusoidally as well. This guy would be a simple harmonic oscillator. So his y height was equal to y maximum cosine omega t plus a phase angle. This was simple harmonic motion for y. We called it x at the time. And then v of the simple harmonic oscillator was negative omega y sub m sine omega t plus the phase angle. And a was negative omega squared y sub m cosine omega t plus the phase angle, which was the same as negative omega squared x as a function of t. Okay. This was that. Sounding familiar? Ish. Okay. So each particle on the wave acts as a simple harmonic oscillator that, now that time has progressed, it has moved to a different part of its phase. So it has a different magnitude. That allows the wave to travel. A plus sign in between here means it travels to the right. I'm sorry, a minus sign in here indicates rightward motion. In this example, our positive direction of motion. A plus sign in there would mean it's traveling that way. And it turns out these two coefficients are crucial in determining the speed of the wave. It's always omega over k. This is true for anything that satisfies the wave equation, which I wrote down incorrectly last time, right? The second partial of y with respect to x is equal to 1 over v squared, the second partial of y with respect to t, right? So all of this was done in Physics 1. Only in preparation for doing it in Physics 2. We didn't need it because then we went to the phasor solution. To change that to electromagnetism, we now simply turns that to an E. And we get the same exact solution. We can pretend that light is made of oscillating electric field strengths that have a planar nature to them, which we could then extrapolate along different directions. And from this, if we apply this to this equation, where we simply turn this into E, right? That's the same exact mathematical solution as we saw in Physics 1. And from that, V is equal to omega over K, just like in Physics 1. Yeah.
On the electromagnetism part, what's underneath the 1?
V squared, sorry, that's the
Okay.
V squared. Yeah, Cody?
So, the double partial derivative of y over x, what's
Uh-huh.
that equation for again?
This is known as the wave equation.
Wave equation, thank you.
The wave equation is general. What it means is any form, anything that's going to describe itself as a wave and have periodic motion that repeats must satisfy the wave equation. There are other solutions to the wave equation, but the simplest is the sinusoidal. And so that's the one we study. Remember, we're looking for a model that's consistent with our data. Is light truly a wave, a particle wave as we learn later? Who the hell knows? Nobody knows. But we have a mathematical consistency if we study light as a particle wave. And so we say, it fits, so it's the best we got. If some data later comes out to show, wait a minute, it doesn't fit in this circumstance, then we'll have to come up with a different explanation. So, we need two graphs to describe electromagnetism, just like we need two graphs to study a physical traveling wave. If I shake a rope up and down, and I want to study that individual piece of the rope, it's just going up and down. But the energy of the wave is transmitting along. So I got a simple harmonic oscillator. So because of that, this V is recast as U. Because that V and this V are not the same. So to avoid confusion, this is the speed of the oscillating element. This is the speed of the wave that results from the connection between oscillating elements. So don't think of this V as that V. So back in physics 1, they called that U. So it would not be confused with the speed of the wave. We are not concerned about this at all anymore when it comes to electromagnetism. We are seriously concerned with this guy. So Maxwell's law, this part of it is Maxwell's law, the Maxwell-Faraday law, I'm sorry, the Maxwell-Ampere law. This guy in combination with the Maxwell-Ampere law. Remember that the integral of E dot ds is equal to the negative change of the magnetic flux with respect to time. Okay. Now the Faraday part of that said that was simply E, right? The Maxwell part of it says this part. If you describe the mathematical B wave as a function of x and t in a similar manner, B maximum sine kx minus omega t plus the phase angle, and you figure out the E, and the book shows you all these diagrams. We're not going to do it, but you can combine this equation, this of Maxwell's equations, with this of Maxwell's equations. There we go. The E version that I erased. Oh, this one. I just replaced the E's, right? And you do this equation, the changing flux of B to get the E's, and this equation, the other one, this one, this equation to get the changing fluxes of E's that result in B's. When you combine the results together, not only do you get V is equal to omega over K, you get V is equal to 1 over the square root of mu naught epsilon naught. Because as you see, these have epsilon naughts in them and mu naughts in them, don't they? So when you take these partial derivatives, what Maxwell predicts of the speed of light is that it's equal to 1 over the square root of these two fundamental constants, mu naught epsilon naught. And this turns out to be 3 times 10 to the 8th meters per second. And the guy's a friggin' genius, he was right. The scientific method says, I'm going to make a prediction that is testable. I think this is true. It fits the data. So I'm going to predict. Back in the late 1800s, they had not found the speed of light yet. The technology had not advanced enough for them to accurately measure the speed of light. They thought they were within 10% or so. They were getting closer. It was a range. Right? And Maxwell says, I predict when you find it, it will be precisely this number. Because I can say that light is a wave, it obeys the wave equation, as long as you put E this way for a plane wave, B similarly for a plane wave, and you follow my equations. This equation and this equation. Remember, this is the Maxwell version of Ampere's law, Maxwell-Ampere. This is the Maxwell's version of Faraday's law. And he was right. And you can follow through in the book how that happens. Those of you taking double E, A-bomb, it goes by a lot of different names at junior level. But you'll see the wave equation writ large in the proofs of this. So rather than take class time for the small amount of people, I used to actually derive it because I thought it was fun. Right? Rather than take class time to show the derivations incomplete and require you to do them, we just deal with the consequences. And so from this analysis, remember the whole point of field theory is that it's a simpler way to explain certain phenomenon than energy theory or force theory or momentum theory or kinematic theory, right? Those 4 different approaches it fits in. But it should be relatable to the other ones. And so the intensity of the wave, what's the upshot of this? We get concurrence with field theory and intensity on other methods. So Way back from physics 1, we learned that the intensity of the wave, another word for intensity is flux, which of course I like to call the four-letter F word of physics, right? Because people have a hard time understanding. It's power divided by the area with which that power transmits through. Right now, as I'm speaking to you, I'm speaking with a certain amount of power in my voice. But by the time it reaches you, that power has to fill all of the area of space until it reaches you. So we saw that for sound in physics 1, the power of the source divided by the area was equal to the intensity you heard. We couched it as decibels on the decibel scale because of the nature of this. But for isotropic sources, point sources, which is what we modeled from physics 1, that means the point source was filling at a certain radius r a spherical surface area. Just because you're only hearing a small part of it, every part at your same distance fills an imaginary sphere of space. And that power has to spread out to cover all that, because not only you hear me, but you hear me and you hear me at the same distance. At the same instant it was uttered, a little bit time delayed. Right? So that surface area is 4 pi r squared. So the power of the source divided by 4 pi r squared should give you the intensity. So measuring the intensity as a function of distance should give you a inverse square relationship. In physics 1, we did this by a sound generating source. In physics 2, you're doing it with a light generating source. Light should obey the same relationship. If you use a point source of light that is isotropic, not a laser, a laser is different. If you use a point source of light like you'll be using in the lab today, then when you graph the intensity as a function of the distance, you should see an inverse square relationship. Now, if he follows the write-up from the book, what he does is have you graph I as a function of r squared. Right? So you're collecting it as a function of r. And there's a difference between lumens and lux, right? So you have to learn the difference in between lumens and lux. And that's written in the handout, but the book records it in lux, right? Which is what is used for near things in lighting rooms, right? If you go at light bulbs, a lot of light bulbs will say lux now instead of that. It's a total kludge based upon the average distance light has to flow in a house, which is generally less than a few meters, right? Some of us have houses that have 4-meter ceilings, right? And sometimes the light's up there and comes down. But the difference in a light bulb at 4 meters and 1 meter at the light bulb intensities doesn't vary that much. So they have this averaging value they call the lux. Right? The write-up describes the difference. Just make sure your light meter is measuring the proper units. They're flux units instead of true power units, unfortunately, right? Lux versus lumens. But what you'll get then, if you graph I as a function of r squared, should be a line. Right? If you graph I as a function of r, it's proportional to 1 over squared. If you get I as a function of r squared, it's a line. And of course, these are written for the lowest level of math students, right? They don't expect you to have calculus. They expect your instructor to level it appropriately to your level. So let's just take a look so this relates to your lab later today so you're not at an end. We'll just go through the actual write-up now. Question? So you don't need to know any of the stuff I showed you for lab. You do need a working knowledge of it for lecture as it relates to the equations, because the electric field itself can be used to calculate the intensity. Now that's not what you're doing in lab, obviously. If we go to the intensity write-up here, light brightness, distance, lab quest. All you're gonna do is take, now use the optics benches, I don't know if he's still gonna do this. The optics benches and the optics expansion kit is a much better way than taping a meter stick to the table. The optics benches have boxes in the back called the optics expansion kit. Okay. And so it looks like, everybody remembers the benches, right? These things just clip onto them. One of them holds the light source, one of them holds the light detector. Okay. It's pretty easy when you open up the box, you can see what they look like. So what it says here is, initial setup, if your light sensor has a switch, set it to 6,000 lux. That's the light detector, right? Connect the sensor to the lab quest and choose new. If you have an older sensor, it does not auto detect. We have new sensors. You have to set up the collection mode as events with entry because it can't measure the distance. You're gonna slide this light meter closer and closer to the detector, right? So it'll kind of look like this. The detector's on kind of a little square mount. So you got your track here, and then the detector's like a little box that the detector sits on. So this guy is the detector. And then there's a round thing here that is the source. And it plugs in the back to the power supply. It has an on-off little toggle switch back here. It's a round one. Flip up, flip down. Turn that on only because it takes a while to heat up, even though it's an LED. It has an operating temperature that evens out over time. Then as you decrease that distance, you have to use the events with entry command. Remember, you have your window, it'll be graphing I as a function of R. It's gonna graph it as a function of R. You can turn it into log or pro into I as a function of R squared by simply doubling that, by squaring that column. Remember how to create a calculated column in log or pro? When you're done, you'll have a column of R and I. Come up here and make an R squared column by choosing that variable and squaring it. Remember, the square function when you write the command is caret 2, right? And that'll create you an R squared column. Then you can put that on the x-axis, display that on the x, and display intensity on the y. And you'll have the linear one that it asked you to create. I remember how to create and calculate columns. It's the simplest one ever. So I over R should go like that. When you change it to I over R squared, it should be a 1. So it says, setup. Set your sensor to 6,000 lux. On the meter screen, tap change the data collection mode to events with entry. So when you do this, when you actually collect the data then, you'll have I and R, and there'll be a button down here that says keep. Once you hit the start button to start collecting data, the keep button will appear. Once you get it to the distance you want, you hit keep, and it'll pop up a little window and say, tell me the distance, because it can't measure the distance. That's what events with entry mean. I'm gonna collect the intensity, but you're gonna have to tell me the distance. So you put in 1.0 meters. It'll still be alive, you'll slide it to 90 centimeters. The room will be completely dark. We have dark out shades in there, right, so you can darken the room. Make sure when you're in adjacent tables that your light sensors face in opposite directions. You don't want your light sensor facing the other way, somebody else's, so he's gonna detect the light from yours that makes it around his own. That can be make a difference. So if you have the tables set like this and like this and like this, right, with 6 tables. So you want your light shooting that way and this guy's light shooting that way, so that your sensors don't detect the other guy's light.
Well, the people next to it.
They're SOL sites.
Damn.
No, what you do then is you do the best you can do.
So then we got like 3 groups, so we could probably do like.
Right, 2 over here, 1 over there.
Or like one.
Or separate a table in between anything like that. So, make sure the filament axis of the light bulb is horizontal and pointed directly at the light sensor. That's easy to do because they made these guys the right height. The filament light sensor should be the same vertical height. Turn down the lights, darken the room. A very dark room is critical to obtaining good results. There should be no reflective surfaces behind you, right? Of course, the wall is a reflective surface, so what are you gonna do about that, right? I tried to argue we needed light absorbing wall paint. But when they found out it was like $1,200.
Super
Yeah,
dark
they
black
decided.
paint.
Do we have light absorbing
wear a black shirt. Stand behind a black sweatshirt. Black book there. So it says start 2 centimeters away until, and watch the display loom. So they're just asking you to check for it. You might get too close. There's a maximum intensity to the light. And it doesn't mention this in here, but you should zero the background light away, right? So basically, I'm sorry, you should cover the light sensor and zero it. And then that would be considered completely dark. Then there's gonna be some background light due to the room. Once you uncover it, even with your light source off, it's gonna read some background light. So some people zero it then and hope the room conditions don't change. So even though it normally says cover it, what I recommend is you don't cover it. You get everybody, all the room lights are down, everything's fuzzy. Nobody's got their stuff switched, nobody has got their own individual light switched on. The background light's the way it's gonna be. Keep your own laptops and stuff away. And zero the detector then. Of course, anytime you zero detector, it's going to take away from the maximum value. If it says it can read 1,000 lux, and there's a background of 50 lux, now it can only read 950 because it's going to set that 50 as 0. Does that make sense?
Yeah.
So then, when you move it in, go until you reach that maximum value. If you get closer, it's only going to give you the max value, and you're going to think that it's still reading accurate. You don't want to start until you come off that max value. Because you will get to a point where you'll be close enough. You won't know until you establish it. Everybody's light source is a little different. So what'll happen is, this is what's happening behind the scenes. Since your detector has a maximum level it can read, you might get to a certain distance where all it's gonna do is continue to read that maximum level based upon how much you took off of your background. That is the no good part of the experiment. If you try to get data past here, it's going to try to fit a curve to it, right, that is unrealistic. And you won't know that unless you know where it is. So let's say your data points look like this. It's gonna try to average that guy in, but he's part of the plateau. What I'm telling you is don't collect that guy. Do a preliminary experiment to move that guy close enough once you've zeroed your lux meter to get rid of that. Now, if Tim doesn't want you to zero the lux meter, it's still okay. But still do that thing and don't collect the data point there because it's gonna try to average that into a curve, right? When we know this guy is flat topped, as we call it, when it's raised to the maximum of the sensor, we want a curve that's gonna fit the data better based upon that. You won't know that unless you slide it forward. Just leave the intensity meter live. You don't have to collect anything. Just start it and move it. The number will keep going up and then it will stop going up. Pull it back until that number drops slightly and use that as your starting point. If 2 centimeters works, great. Generally, it's farther away than that. Generally, it's farther away. Yeah.
Since we're assuming we're all gonna be doing our experiments at the same time, so everyone's lights are gonna be on at the same time. So wouldn't it make more sense when you zero it to cover your own light bulb and make sure everyone else's light bulb is on, since you expect them to be on during the experiment? So then that would cancel out what they.
If you want to go to that level of, yes. A lot of things make more sense if you're going to coordinate together. It make more sense to go to totally different lab rooms, right?
Yeah.
But that's the only one with the dark codes.
Which one? The one we're in. Alright, okay.
Okay. Wait for the displayed value to stabilize, then hit continue moving. There is a maximum value you want to fit the curve to. So the last of this is to get a model parameter A and the leftmost Y point and the right and the leftmost X value. So it says continue moving the sensor in 1 centimeter increments until the light sensor is 10 centimeters from the light source plugged in. Get as many points as you can. Right. Get as many points as you can. They go from 2 to 10 because some people have to have that. Start wherever it starts, doesn't flat top, and get as many as you can. 1 centimeter increments are fine because what it actually does, remember, there's a number built into that light bench, into that bench, right? So this bench has a meter stick built into it. These clamps that go over them have a little indicator position that will point very accurately. As you slide it, the center of that will be noticed by that thing. So you don't have to guess where the front of the sensor is. It holds the sensor at the point where this clamp goes in, and it will read the number for you very precisely from it. So then, of course, you just subtract the numbers from the 2 points, these little clips that hang over the edge, point to that meter number. So it's very handy that way. That way you don't need a meter stick. If he wants you to use the meter stick, then just use the meter stick. Take the meter stick to the table, take the light sensor to the table, and take your light source, but this is much better. Analyze.
It generally lets us do things that are much better.
Examine the graph of light intensity versus distance. Does it appear to be consistent? How can you tell? Compare your data to a model. To examine the displayed graph, tap any data point. As you tap each data point, the light intensity and distance values are displayed to the right of the graph. That's where it is. Tap the leftmost point on the graph. Record the coordinates of that point on your data table. You will use this later in comparing your data to the model. Plot the equation y is a over x squared. Right? This is where you do the r squared stuff along with your data. By adjusting a, you will change the overall scale of the model. Only if the model and the data are consistent should it be possible to adjust a single parameter a so the model comes very close to it. So in model mode, you're saying, I want you to have this shape, and I'm going to tell you exactly. What we've been using primarily is curve fit. Right? Curve fit, we've been letting the science, letting the math determine for us what the best curve fit is. In this one, it's a model. You have to base models on parameters. And so basically by choosing the leftmost point and the rightmost data point, you're saying, I want you to definitely go through here. You're overriding the software, which is trying to fit the data points to overallness, right? So in the model option versus the curve fit option. So it's telling you to model this because we're very confident in those 2 data points and we want to use them. So if these were what my data points look like, right? And I choose curve fit, and you say inverse square. It's gonna fit the best inverse square, and it may be below this guy and above this guy, for instance, if that's what it says. Because the curve fit is averaging every point equally, right? The model, on the other hand, when you model it, you pick your points and you say, go through there. I want you to fit those points. And so as a result, it might miss the other points, but it's going through those 2 points. Okay?
Why we want the model over there?
Generally, the results are better with the model method when you can guarantee your endpoints of values, right? And the discrepancies in between. What is really, I didn't talk to the publishers of why they did this one versus that one. My guess is they just wanted you to show that sometimes scientists use endpoint modeling and sometimes they do curve fit modeling. I can't think of a scientific reason why model would be better here than curve. Maybe Tim can, I don't know. But I can't think of a reason other than the fact they probably want to expose you to, there are times when the endpoints are better because you can calibrate right to the endpoint. You gotta figure out where to calibrate your instrument. You can't calibrate at every point along the line. You gotta calibrate it at certain known values. So maybe you calibrate at this value and this value, so you're saying, damn it, those are right. But the calibration's gonna be a little off at values in between. I can't possibly record every value accurately. Nothing is that, I don't have the money to make an instrument that's accurate. So I have a 2-point or a 3-point accuracy depending on how close you are. And the manufacturer guarantees, yes, if you do a 2-point, those points will be within blah, 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 so many 9 and 9 difference, as we call it. Basically, statistically negligible off. But every point in between, I can't guarantee it because I can't guarantee a perfect instrument that scales linearly or quadratically or whatever.
Makes sense.
Makes sense? There's a physical limitation. So that's my guess why they do it this way. And then it tells you exactly what to do here. He likes to have you do the analysis exactly as written from what I understand. So you just follow it. That way he doesn't have to change it. When I teach it, I model it the way I want it to be presented, which I think is the easiest way to understand, which sometimes this isn't. And of course, remember, this is written to be able to be done by anybody. This doesn't require any calculus, any understanding of differentials. And I can up the level, so to speak, and have you do an analysis more appropriate to your math.
This one is curve fit under it. So that's why I specifically, but I understand why people, especially when you have multiple sections, they don't do that.
I don't know how to integrate. It's not like I just took a test on double and triple intervals this morning.
So that's basically what your lab today will be about. So again, the data collects really rapidly, and it doesn't take all that long, but the whole point of it is stay in lab, work through the stuff, so you're not doing like today and waiting until midnight to submit your lab report the next week. How do I know? Because I'm a teacher too, and I did the same damn thing when I was a student. And physics was my number one, right? It's like all the other classes could wait, and I did physics, and my physics lab still waiting until the last minute. But mine was where I kept thinking about it, and was like, what else can I put in there anyway? Paralysis by analysis. Any questions about that? Any questions about the materials we saw in today's study? And again, they show you how you can get the intensity from the maximum strength of the electric field. We'll show you those equations when we get to them. They're very simple equations. 1/2 epsilon naught E squared, right? You don't get much easier than that. But we'll show you, again, that comes out of Maxwell's equations, how you can figure out the intensity from the strength of the electric and magnetic fields. It's a very short and sweet understanding based upon a difficult math.
So how can we use partial differentiation for a lot of the stuff that was in the lecture? Like, does that just come from the harmonic oscillator?
It comes from the wave, that wave equation says. That wave equation basically has been mathematically proven to describe any periodic function. So any periodic function that is a planar in nature has to validate that. And the simplest validation is the sine or cosine wave. And so as a result, we modeled many things out of that because they fit the wave equation. Easiest. Remember how I told you about the sawtooth? That's a periodic function. Remember I told you the square wave? That's a periodic function. So those guys have to fit the wave equation. So this guy fits the wave equation, this guy fits the wave equation, this guy fits the wave equation. But these are harder to describe because you've got this discontinuity in between. So you've got to deal with these transitions, and you've got to do it piecewise forever to get this periodic function to show up. This guy is continuous, so he's much easier to describe as a periodic function. Right? Not that these don't have their uses, as I showed you last time. It's simply that they're more mathematically complex to solve, so we stick with these. Okay? It's like cart before horse. Do we do it because it's the way it is, or do we model it that way because it's the simplest one to solve? We model it that way because it's the simplest one to solve, and then we look for consistency and say, yay, we got it right. We don't have to go to more complicated. So let's take a look at the chapter 32 notes, and then we'll take our break. Let's open chapter 33. Oh, it's a nice one. Long time ago. Here they were. Topics of chapter 32 are Maxwell's equations and displacement current. We will ignore all sections of the paper book past section 3. Section 3 deals with ways we have different types of magnetism, right? Paramagnetism, ferromagnetism, and ferro, and basically magnetism is explained as well through this, but they don't take, because the math gets much more complex. It basically tells you 3 different ways magnetic materials behave. The key to doing well is proper depictions. Generally, we will be dealing with circular parallel plate capacitors to keep the math simple. Inside a uniform flux or electric field as a function of time, the radii of the left-hand side and right-hand side are the same, and you use R only where it appears because of the area. So remember, these equations have a flux integral on one side and a path integral on the other side. This is talking about the relationship of the radius of the flux integral, the fluxing region, and the radius of the
surface where we're measuring the magnetic field or electric field. So, path integral of B dot ds is equal to, we're only gonna do the Maxwell part of it. This is a flux integral, right? It's an area, right? This is a path, but it's going to be a circular path. So if we have our parallel plate capacitor with an E going through it like that, there will be a changing flux with respect to time, and there'll be some radius at which it stops creating potential because we're out of plate. If we take a point anywhere in here, and now this is the path of the BDS, the radius of this guy will equal the radius of this guy as long as we stay within the parallel plate capacitor. So the circular path that is used here is where we measure B at. And we've seen this before. This is where the area ends that creates flux. And what this statement says, as long as we're inside the parallel plate, the radius that creates the flux area is the same as the radius of this path. We've seen this before, right? Anytime we have that, it's always, is it in there? Recall the Ampere's law, 2 ampere, right? What if we only wanted the current within a small section of that wire? Say this region, right? Then we only went out to the radius here, but we only got I enclosed. Instead of all of the I, we only got the I enclosed, because that was where the current stopped that created the magnetic field there, IBS, right? So the radii had to match. But once we got outside, this guy stopped where the current stopped. Then we went to I total. We didn't add more I because there was no more I to add. But the radius increased to the radius of the Amperian loop, which was now larger than the radius that created the current. See where I'm going with this? As long as I'm inside, the radius that creates the flux area is going to be equal to the radius of the path of integration on the left-hand side. But once we go outside, for our loop, it's not an Amperian loop, less than or equal to R of the capacitor, then those R's are equal. But for R of the loop greater than our capacitor for the flux stays the same, and this guy becomes the R of the greater distance. Just like we did here. We can't increase this guy if we're out of flux generating region. Once we get outside of here, then that R is different for the path, because now the path is out here. So if R of the path of the area exceeds R of the loop, so R of the loop exceeds R of the area, then the flux region stops where the area stops. But the path is always measured where it's at. And again, we've seen this several times already, but it's just now we have two different integrals. That I doesn't have to be an integral. Sure, we made it an integral j dot dA sometimes, and remember how we set the limits of the j dot dA integral where we were curious as to what current was? Same thing. Outside the radii of the LHS is where we measure the B field at, and the radii of the RHS is R, the radius of the flux generator. It's actually a little smaller. So inside the uniform flux or electric field as a function of time, the radii of the left-hand side and right side are the same, and you use R only where it appears because of it. Outside, the radii of the left-hand side is where we measure the B field at. And the radii of the right-hand side is R, capital R generally, the radius of the flux generating region in total. Because lowercase r is greater than uppercase r.
if it is a non-uniform, an R function, then we convert the area integral into an R basis integral. It should be an I in there, basis integral, right? So, and we've done this before. It's the same damn tricks we do over and over again, right? If I was not a function of R, when we had mu naught I enclosed, we just took I enclosed as some ratio of I total. Maybe it was all of I total, maybe it was a portion of the radii, right? Because it was inside. But if I was a function of R, then that I enclosed had to be converted to a J dot dA. But J was only a function of R. So we had to turn that into a 2 pi R dr. And the A integral became an R integral. Remember that? So what's going to happen here? If E is not a function of R, then this term, which is the displacement current, will be a constant or a ratio of how much of it we actually have. So the ID enclosed, they don't write it that way, but I like to remind people that. ID enclosed, right, which is just like I enclosed, is some function of the total I sub d. If it's the tire radius, it's all. The ratio is 1. Other than that, it's a fraction or a portion, depending on the radii. But if not, then we've got to find a way to convert that flux into a radius-dependent integral. Okay? So then we're going to get E dot dA cosine of the angle between them as a function of the area, right? But what if they give you E as a function of R? Then E will go in as a function of R. You'll have to convert that to an R, and because it's a circle, what's dA going to be? 2 pi R dr. Because we're keeping the applications as simple as we can. The ones we've seen before. So when it comes to this, remember, we said 3 ways to create a changing magnetic flux with respect to time. Number 1 was B, number 2 was A, number 3 was theta. And we said ignore that, right? And sometimes the A had to be converted to an R integral, and sometimes it could stay an A integral. Right? Depends on whether it's uniform or non-uniform. Guess what? D flux E dt. 3 ways. Number 1, E changes with time, A changes with time, theta changes with time. Again, we're going to ignore the theta changing with time one. And the A will have 2 possibilities, either where we have to convert it to an integral over R if E is a function of R, but if E is not a function of R, we'll just keep it as an integral over A. But the first part has some other complications. Because what if instead of giving us E, they could also give us V instead? Because aren't electric fields related to electric potentials? They are. And so the question is, how do we turn an E in that equation into a V? You already know the answer. What turns V's into E's? Or vice versa? Faraday's law. And what if we're given I instead of E? J dot dA is a possibility, but it's more likely it'll come through the resistance route. R equals rho L over A. Because after all, what is rho? What's the definition of rho?
Isn't that density? Like,
It's the resistivity.
Yeah, resistivity.
But which 2 physical quantities is it a ratio of? So we can end up having either the resistivity be a function of E, which it is, that's by its definition, or the current being a function of the resistivity based upon the resistance of the resistor. So it comes into a bunch of different little substitutions, depending on which path we take. And then, you bet it, the E here could also be a function of R, so you might have to run back here, in the most complicated forms of it, right? I promise not to make these anything more than they absolutely have to be. Doesn't mean they're not gonna look harder, but they will always be the simplest possible variation of all of these types. I gotta show you an example of each type, at least one of each type, because I keep them all open as possibilities on the final, because you don't know which is important to your field going forward, if any of them are. But it's nice to be able to see that. I've already knocked out the thetas, so we don't have to deal with those, because those lead to the more mathematically complex ones. Unless you go to engineering, then they say, hey, here's the solution, our physicists worked it out for us, isn't that nice?
Thank God.
Yeah, but electrical engineers are kind of that branch, right? You get a lot of people going into management who are electrical engineers because they speak the language of engineering, and to some extent, they speak the language of physics. So when you need somebody to keep your engineers and your physicists from butting heads, they call in the electrical engineer and say, hey, this is what he means, this is what we're going to interpret. Okay, no. So basically, that's what the second part of this says. What if we're given dV by dt instead of dE? We use Faraday's law, blah, blah, blah. And we'll see examples of all these in the next couple of days. Not all at once, because these are relatively lengthy, as you might imagine. It's noon, we'll start at 10 after. I do remember we have a second hour today. Yay me.
No, we're done for the day.
We're
I
done.
always forget.
It is? This is the one, okay.
Glad to do it early here.
Daylight savings time happened in the middle of class again?